So this video will look at many examples that use continuous growth or decay and compare it to the non-continuous exponential functions that we've been dealing with. So 4.5 looks at the number e, and the number e is just an irrational constant. It's called Euler's constant, Euler's number. It's approximately 2.7, but it's like pi. The decimal goes on with no pattern. It never ends. It's called the natural base, and it's used a lot in calculations with growth or decay to represent it, that it's a continuous growth, not just a one-time at the end of the year, at the end of the day. It's happening continuously throughout that unit of time. And before, when we did our exponential functions, we had a non-continuous growth rate or decay rate in which we took one and either added or subtracted the factor or the rate to get the factor. And now instead of doing that, we're going to use e, and we're going to give e a power. And depending on whether it's growth or decay, that power, that k, it'll either be e to a positive decimal if it's growth, or it'll be e to a negative decimal if it's decay, and then t will appear as a variable on that exponent. So just for some examples to writing these, here at the bottom, regardless of what a is just some initial value, because writing that will be the same as it was before. If you had a problem that had 5% continuous increase per year, then the setup would be some initial value times e to the 0.05t. You just take 5%, get the decimal form of it, and that becomes your exponent on the e value, and then it gets a t multiplied beside of it. For 23% continuous growth per year. And it could be per year, per day, per minute, per hour. It'll just be per some unit of time. But the word continuous makes us use the e. So for 23% continuous growth, we would just do some initial value times e, and then our exponent would be 0.23t. Okay? If it's a decrease or a decay, a decline, a shrinkage, but it's continuous, now the k value will be negative. There's no subtraction to get a new factor. So a 15% continuous decrease would just be some initial value times e to the negative 0.15t. A 2% continuous decrease would be some initial value times e to the negative 0.02t. So all you're doing different, instead of a factor where you have to add or subtract to indicate a growth or decay, you just take the decimal form of the percent, and then you change it to a decimal, and then you put it as a power on the number e. E becomes the base instead of a factor, and then it just gets the exponent of the increase. And then if it's a decrease, it'll have a negative exponent on it. Okay? So here's a few examples comparing some of the things that we've done before. So like this first one. It has an initial value of 50, and there's 50 things. But the fact that it has e means it's going to be continuous growth or decay. And if we pull this k value, this 1.05, the decimal 1.05 as a percent would be 105%. So this is representing continuous growth of 105%. Right, the next one, second one, it has an initial value of 100th. But if we focus on this k value, this negative 0.02, the fact that it's negative and that it's on e is a continuous decay or continuous decrease of, and 0.02 as a decimal is 2% as a percentage, remember, multiplied by 100. And so this negative 0.02 exponent on e is representing a continuous decrease of 2%. Okay, same for the next one. This third example, initial value of 25, and e has a power of 0.032t. So if you take 0.032, change it to a percent, multiply it by 100, move the decimal place right twice, it's a 3.2% continuous. Again, the word continuous is key here. some kind of continuous growth or increase for this function. Okay, the next one, because there's no e, is not continuous growth. So this is non-continuous, and it's just our regular, whatever the per unit time was, like 0.12, that was a decay factor, if you recall that from the previous sections. So if it was a decay factor of 0.12, the way that we got that was subtracting it from 1, and that gave us the decimal 0.88. So that told us that we had an 88% decay rate, whether it was 88% per year, 88% per day, 88%, whatever the unit of time was, it was an 88% decay rate. So that, again, that's not the continuous kind, that's just our regular exponential decay. This fifth example, there's no e here, so this is also a non-continuous example. The factor is over 1, so this is a growth factor. And the way that we pull the percentage from that is subtract the 1. So 1.137, if you subtract the 1, we're left with just 0.137. And to change that to a percent, again, multiply by 100, move the decimal right twice, and you get a 13.7% growth rate. Again, the per unit of time will depend on the problem. But it's not a continuous growth rate, it's just a normal exponential growth rate. This last one, the base is 2. The initial value could be considered 1 if you need to think of it as something. But the fact that this base is 2, it's not e, it's kind of like a growth factor of 2. So the same like we did before, if we subtract 1 from it, we'll get that this is representing 100% exponential growth. Okay, so the bottom 3 examples were your normal growth decay in the exponential sense, and then the top 3 examples were those ones that were representing continuous growth or continuous decay, because it has that base of e, and you're just putting the decimal form, whether it's positive or negative, on the exponent. Okay. Here's another word problem that appears in this section. So let's say you started with a town with 3,000 people at the initial year of 0, and you want to look at a population formula with a few different scenarios. So for the first one, if you knew the town's population grew by 200 people per year, if all you know is the number of people it increases per year, that is going to be a constant rate of increase. It's not even really a constant rate because it's not a percentage rate, it's just a constant increase in people. So that's going to make this a linear function that we'll create. So for this first one, started with 3,000 people, and we just add 200 people per year, so plus 200t. Okay, if it grows by 6% per year, this is exponential growth, in which we did initial value times a growth factor to a power. So our population function here is 3,000 initial value. 6% growth is a 1.06 growth factor raised to the t power. Okay, so that's just your basic exponential growth. If you have the next example where it grows at a continuous rate of 6% per year, remember 6% is 0.06 as a decimal, and because it's continuous, you were going to use e. So our population function will start with 3,000 people, and then we'll multiply e to the 0.06 t as our exponent to indicate that it's growing at a continuous rate of 6% per year. Okay, the shrinking population will model the growing ones, but at the decaying rate. So if it's shrinking by 50 people per year, that's a constant decrease of people per year. So this one's going to be linear. So our population starts with 3,000 people, and you'll subtract 50 times t for t years. If you're shrinking your population by a constant 4% rate per year, this is just exponential decay of 4%. And remember, if you're shrinking 4%, that's where we think of that as 0.04 as the decimal. But if we're shrinking 4%, we're actually keeping 96% year to year. And the 96%, the 0.96, is our decay or our growth factor that's in between 0 and 1. that we put into our formula. So population here is 3,000 times the decay factor of 0.96 to the t power. The last example here is it's shrinking at a continuous rate of 4% per year. So 4% is 0.04. The fact that it's shrinking, we're going to have a negative exponent on our e value. So our population formula is 3,000 e to the negative 0.04 t. And again, all that negative is indicating is it's a decreasing rate, and the 0.04 is the continuous rate of decrease. And that would be the function for that one. Okay. So here's another word problem with another continuous rate. So you have a town that starts with 10,000 residents, and it's going to grow at a continuous rate of 4% per year. Again, the word continuous is key in writing the formula because this needs to show a continuous growth rate. So we'll use E in our formula. So 4% is 0.04. It's growing, so our K value, our exponent on E, will be positive. And our formula would be 10,000 e to the 0.04 t. Okay, if we would like to predict the population after 5 years, we'll just plug in a t value of 5. So our population in 5 years would be 10,000 e to the 0.04 times 5. You have to be careful when you type this into the calculator because e needs to have the product of an exponent of 0.04 times 5. So just be really sure that you use parentheses around that exponent on e so it multiplies the 0.04 times 5 in the exponent that's on e, or you'll get the wrong calculation. So if I do 10,000 times e to the 0.04 times 5, I get 12,214 and 02758 is the decimal. So whichever it asks you to round to, it's around 12,214 people 5 years after this population formula started. For the last part of this question, it's asking you to find the annual growth rate. So it's telling you that there's a yearly continuous rate of 4%, but to find the annual growth rate, that's going to drop back and look at the normal non-continuous growth rate. So we had 10,000 e to the 0.04 t. If you remember the growth function from before, it's just an initial value times a base to an exponent. So if we focus on the fact that the b was our growth factor, we can take this e to the 0.04 and actually calculate e to the 0.04 power and get a decimal representation for that, because e is just a number. And if we do that, we get 1.040810774. And if that's our growth factor, like we had before, then you can subtract it away from 1 and see that a 4% continuous growth rate is equivalent to a 4.08% annual growth rate. And the regular growth rate has to be a little bit bigger to be comparable to the continuous growth rate, because the continuous growth rate grows a little bit faster. So the annual growth rate is just a little higher, and it would have to be a little higher to be able to match the continuous growth rate. So if you have to find the annual growth rate from a continuous, you basically just pull in the power on e and calculate an e to that power, which would be a growth factor or maybe a decay factor if the exponent on e is negative, and then you'll just convert that to a percentage growth or decay like we had before. Okay. Here is a decay example with continuous. So we have a radioactive substance that's decaying at a continuous rate of 14% per year. 50 milligrams is the initial substance present when this formula was started. So we have A equals 50 times, right, continuous rate of 14%. So 14% is 0.14 as a decimal. And because this is a decay, then we're going to make sure that the exponent is going to be negative whenever we attach it to e. Okay, get rid of that. So 50, our formula for the amount present a, is 50e to the negative 0.14t. And that's the formula. There's nothing else to convert, no decay factor like on the other decay problems. Continuous decay is just a negative of the percentage on the power of e. So to calculate how much is present in 2019, that would be 10 years after the initial 2009. So we'll just take 10 and plug it in for t. So 50e to the negative, 0.14 times 10. But again, make sure that that negative 0.14 times 10 stays in the power of e. So calculator-wise, it would be 50e to the quantity of negative 0.14 times 10. E negative 14. So I get that in 10 years, there's 12.3298 milligrams of this radioactive substance. And it's decay, so over time it should be going down. Last question says, estimate when the quantity drops below 5. So this is where it's giving you the amount value. So you're trying to find when the equation of 50e to the negative 0.14t equals 5 milligrams. And this is where we're just trying to solve for the exponent and the exponential function. So at this point, we're going to just use a graph and figure out where those two decay. Because, the decay graph will be like this. 5 will be here. We're looking for that point of intersection for which it drops below 5. So if we do that, we put 5 as one of the equations, and then we put 50e to the negative 0.14. We have to use x on a calculator, and then graph those two. Again, it doesn't really matter the order, but if we graph those two and see where they intersect, you get a t-value of 16.447 years after 2009. So the question could ask you for the t-value, but it also may ask you for the year. So if this was starting in 2009 and we added 16 years later, the year answer, and I think it has you round to the nearest year, so this would be just adding 16. You'd have to take 2009 and add 16, so that would be in the year 2025. So again, it could ask you for the t-value or it could ask you for the actual year, so just pay attention to what the directions have you solve for in the problem when you do your homework. Okay. So here's a question that asks you to compare two cities and be able to explain which one actually grows faster. So you have city A has a continuous growth rate of 15% per year, and city B has an annual growth rate of 16% per year. So the 16% per year annual is what we dealt with for the beginning of this. It just grows at 16% per year. 16% growth would be 1.16 as a growth factor when we created our exponential function. The continuous growth rate of 15% per year in the formula, regardless of what it started with, was E and the power would be 0.15t. And if you'd like to compare that to what that is in the sense of annual growth rate, you're just going to pull off the e to the 0.15 power and actually calculate the value for e to the 0.15 power, and it's positive growth rate, so we're using a positive exponent. So if I raise e to the 0.15 power, I get the number 1.161834. The decimal goes on and on. But that's the comparable annual growth factor for the continuous growth rate of 15%. And the 1.1618 is a bigger growth factor than 1.16. So the growth rate from the continuous one, the annual growth rate is actually 16.18 or 16.2%, and you're looking versus a 16% annual growth. So in the question of which city grows faster, we're going to have to go with city A, even though it's a lower percentage rate because it's continuous, it's growing faster than city B. So again, this is just comparing a continuous growth rate to an annual growth rate, and the continuous growth rate, especially if the numbers are the same, the continuous one grows faster because it's growing continuously that entire year. Every minute, every second, every fraction of the second, it's growing. So it grows a little bit faster than regular growth rate. So this last example, there's an epidemic. Yeah, welcome to flu season. And you have people in a city and they're infected by the disease, and the rate at which they're being infected, it has a continuous rate of 60% per day. Even though it's day, that's still your percent unit of time. So there's nothing to really do for this, no conversion, because we're going to predict in days and do a daily percentage rate. So this time just happens to be in days instead of in years, as a lot of the questions are. So the fact that it's a continuous rate of 60 per day, the number of people infected would be some initial value times e to the 0.60 t, because this rate is 60% per day. This question starts so saying if 10 people were initially infected, so that would make our formula 10 times e to the 0.60 t. How many would be infected after a week had passed? Well, since our time is in days, a week is going to be a t value of 7 days. So we'll just plug the number 7 in for our power, and we get 10 e to the 0.6 times 7. So again, whenever you go to calculate that, make sure that you do 10 e and then the power is the product of 0.6 times 7. And you get 666.8633. I don't know if you have to round that to 667 people, because that's the whole number it would round to, or if it asks for a decimal, just watch the directions. But you just plug in 7 for 7 days. The next part says, by what daily percentage does the number of infected people grow? So this is looking for a daily rate instead of the continuous rate. So if you go back to our equation, where it was e to the 0.6 t, again, to get that daily rate instead of the continuous rate, we're going to simply pull that e to the 0.6 power and calculate e to the 0.6 to get the number 1.82211188 as the daily growth factor. And then we pull, subtract the 1 and only focus on the 0.822. So that would indicate an 82.2% daily growth, or the daily percentage on which the number of infected people will grow. So it's a pretty high growth rate there. But you're taking the daily continuous rate of 60%, putting 0.6 on an E, and then that will give you the exponential daily growth rate instead of the continuous growth rate. So that is the number E with functions.